Okay, let's continue for a discussion about section 1.6, the magnetic field. In this section, we present another experimental law known as the Ampere law of force, which is analog to the Coulomb's law, and it was used to introduce the concept of magnetic field intensity, magnetic field and magnetic field intensity. What is the source of magnetic field? As I already mentioned, the principle, the fundamental source for magnetic field is electric current. As long as there is electrical current, it shall be accompanied with magnetic field. So the famous Ampere's right-hand rule tells you that if you have electrical current flowing in the direction of your thumb, then it will produce magnetic field. And the direction of the field follows the rest of your fingers in this way, in the right-hand school fashion. And vice versa, which means if you have helical or spiral or currents in spirals, it will produce magnetic field following the direction of your thumb. So as long as there is electrical current, you will have magnetic field. Of course, there will be other sources that can produce magnetic field, as we discussed along the Maxwell equations. But the first thing first, the fundamental source for magnetic field is electrical current, simply as the fundamental source for electrical field is what? Is electrical charge. Okay, so rho produce E and I produce H. And similar to the presence of electrical field, which produce the so-called electric force, the magnetic field in certain conditions shall give you the so-called magnetic force. One example is magnet. So as you grow up, of course, you have played with magnet. Okay, some magnet will produce very strong magnetic force. On what? On another object that produce magnetic field, right? Simply like that the electrical force acts on charged particles. Magnetic force acts on objects with magnetic field, all right? But there are some differences among how electrical force and magnetic force works. So that will be our principal concerns in today's lecture. All right? So as I already mentioned, the principal source for magnetic field is electrical current. There is one thing important about electrical current, that is, the electrical current must flow in a loop, which means there is no ends for electrical current. 电流是没头没尾的，它一定要绕一个完整的圈，没有办法绕一个完整的圈就不会有电流。Okay? So if we talk about electrical current, we have something in mind, that is, electrical current must flow in loops. So as the figure shown in this slide, the electrical current loop can be divided into many short sections. as the plot suggests. And each small section of current shall produce magnetic force, and the way it produces will be discussed later. However, as I already mentioned, magnetic force only take place when there are two sources of magnetic charge, magnetic field, not magnetic charge, magnetic field in presence. So, as this figure suggests, we have two current loops. You have two current loops. Each current loop can be divided into many short sections, which is valid for this one, loop 1, which is conduct a current of I1. Here is another loop. Loop 2 conducted with currents I2. And the small section in loop 1 may produce an electrical field acts on a small section in loop 2. And one concept, even though that the act of electrical field can be interpreted as interaction between small sections. However, the overall effect should be viewed as a whole. That is, the magnetic force experienced by a current loop, shall be the summation, shall be the total sum of individual section within that current loop. Okay, so whether you can, even though that in our analysis we can discuss, we can calculate the magnetic force between small section in the two loops, the overall effect must be viewed as a whole, so that they can, so that the overall effect can make sense in terms of laws of physics. 所以即便我们在分析的时候，是用小线段之间的磁力、磁作用力影响或磁场影响来去做细部的计算，但这些细部的计算没有办法单独成立，它必须要被整体加总之后，才能够看出它在实际物理世界中的作用情形。所以这边要小心一点。那当然我们等一下也会再描述一下需要注意的地方。Alright, so as shown in the example in previous slides, say we have two loops, loops 1 and loops 2, and loop 1 is divided into m sections, while loops 2 is divided into n sections. Therefore, we have many pairs of interaction between the many sections in the two loops. So overall, we have m times n pairs of magnetic force interactions. Now, these equations address the magnetic force between two short sections of current carrying of two short current carrying sections. And as you can see, it's pretty much like what we have from Coulomb's law for electrical force. However, they have certain differences. This equation is referred to as the Ampere's law of force. Ampere's law of force. So F1 is what? F1 is the force experienced by a section in loop 1 due to the presence of currents in loop 2. So you see here we have dF1, here we have dL2, means that the source for this magnetic force is located in loop 2. Not that there is D everywhere. Why? Because we divide a complete loop, loop 1 and loop 2, into small sections. So the force is only a part of it. We only discuss a part of the force, a part of the sections in the loop. So the D refers to that we are talking about the influence or the impact of very short sections. All right? So I1 dL1 is what? It's pretty much like Q1 as we observed in Coulomb's law.应该是吧，没记错吧？哦 ，OK， 好，就是库伦定律嘛，哈 ，That's Coulomb's law. So here is Ampere's law of force. So dF1 is the force experienced by a short section in loop 1, that is dL1. And the currents in dL1 is I1 dL1. The currents in loop 2 is I2 dL2. It's I2. And A21 is the line pointing from the section in loop 2 to the section in loop 1. Okay? So you need to be a little bit careful about this. This suggests the lines from a short section in loop 2 to a short section in loop 1. Or is the distance between the two short sections. K is a constant, which is related to the material property, pretty much like 4 pi epsilon, as we've seen in the Coulomb's law. So by writing the two equations, the Coulomb's law and the Ampere's law of force together, you can see there are some energy. There are some similarities between the two. They are proportional to the source, the product of the source. They are inversely proportional to the square of distance. They are related to the environment, related to the material property. They are related to the direction between the source and the observation point. However, they are not in the same kind of formula, right? There are certain differences. Can you point out the difference among the two equations? The most important difference is, unlike Coulomb's law, which is acting on the line that joins the observation point and the source, the magnetic force is not in the direction of the vectors that are joining the source and the observation point. In fact, it's perpendicular. It's orthogonal to the line. It's orthogonal to A21. Why? Because the operation, cross product operation over here, they are actually two cross product. They have actually two cross product. So, yeah. I1 I2 对，是存量，谢谢。本来应该是向量了，但是因为有 DL1 跟 DL2 之后，你就可以把 I1 I2 改成存量了，谢谢。All right, good point. Okay, so we shall continue about our discussion about the difference between Ampere's law of force and Coulomb's law. So another similarity between the two law of force is that if there are two current loops, loop 2 will act on loop 1, the loop 1 will act on loop 2 as well. So you can also write another equation that is dF2 equals to I2 dL2 cross KI1 dL1 cross A12 divided by R to the square. Will be dF2 equals to dL1. What do you think? Will it be the same? Well, for Coulomb's law, for electrical force, F1 and F2 will be of the same magnitude, but it will be of opposite direction. And for magnetic force, as you can see the components in the equation, they suggest that the magnitude of dF1 and dF2 should be the same, right? Because everything in the equation are the same for the two equations. However, how about the relationship of direction for the two force? Well, in fact, they are neither of the same direction nor opposite direction. The direction can be quite strange. Why? Because of the cross product. All right, we will see example in following slides. 所以这边看到电作用力的话，它的两个作用力会一样大，然后方向相反。而磁作用力呢，从事实上来看，它们也应该是一样大的因为参与的那些参数的数值都是相同的。但是比较好玩的是，磁作用力的 dF1 跟 dF2， 它既不是相同方向，也不是相反方向。事实上，它们的方向可以是很奇怪的我们等一下看看。Alright, for free space, k, the constant k, equals to mu sub 0 over 4 pi. So here is another similarity as we've seen from the Coulomb's law. This suggests k, which is 4 pi over mu sub 0. 是吗？错了。It's mu sub 0 over 4 pi. Is related to the total steradian in a spherical space. Is related to the magnetic property in this space. This is the permeability of free space, while this one Epsilon sub 0 is permittivity. 一个叫介电系数，这个叫介磁系数。Permeability is referred to as 介磁系数。 And the value of that is 4 pi times 10 to the minus 7, or 1.256 times 10 to the minus 6, which is, as the number suggests, a small number. All right, so next let's look at the Ampere's first law. As I already mentioned, because of the cross product, the two cross product in the Ampere's first law equations, the magnetic force is not acting on the direction, not on the line between the source and the observation point, which means it's not in parallel with A21 because of the cross product. Then what is the action, what is the direction of the force? Well, you can just follow the equation and use your right hand to find out. All right, so in this figure, suppose we have DL1 over here pointing up, DL2 over here pointing to top left. So let's see, A21 is pointing from point 2 to point 1. So it's in this direction. So the first cross product is DL1 cross A21. Then what is the action? What is the direction? L2 cross A21. Then the direction of this new vector is pointing out of the screen in this way. And this vector will be cross product with DL1. So DL1 is pointing upward, and it goes to a vector pointing out of the screen. So the magnetic force, DF1, is pointing in which way? It's pointing to the right. Okay? Don't be shy, use your right hand and follow me. First, DL2 cross A21 is pointing this way, then DL1 cross here is pointing to the right, right? So DF1 is pointing to the right, which is neither in parallel with A21 nor perpendicular to A21. 它既不是平行，也不是垂直，就是一个向右的方向，有没有？自己要动一下右手哦，我都没有看到你们动右手自己要验证一下 ，OK？ Okay, another interesting thing is if you do the calculation in a reverse way, which means you are finding dF2, that is the force, magnetic force, due to the presence of DL1, the currents on DL1 and acting on DL2. What happened? So for the calculation of DF2, we will replace A21 as A12, DL1 here and DL2 here. So let's try again. So DL1 cross A12, DL1 cross A12, pointing this way. It will give you a vector that is pointing into the screen in DL2, right? So pointing into the screen. Then DL2, okay, DL2 cross the product of the original one is this way. Well, for DF2, it's in parallel with A21, right? You should check again with yourself. But anyway, DF1, which is pointing this way, DF2 is pointing this way. Their magnitude should be the same because every parameter within the calculation are the same for the two force, for the calculation of the two force. However, one is pointing this way, the other is pointing this way. What is the problem? Well, that's a serious problem. What kind of serious problem? The third law of Newton's force is violated. What it says in Newton's third law of force? 牛顿第三律说什么？作用力与反作用力大小相同，方向相反嘛。那我们刚刚算出来了 ，F1 是朝右边的 ，F2 是朝左下方的，方向不同啊，没有相反了。大小虽然相同，但方向没有不同，那怎么办？要求啊，但是我们刚刚在一开始第一页、第二页slide时有讲过嘛，这个计算必须要整体来看，不是我们刚刚只是做一个微观的计算你的整体效果是整个 loop 对 loop 的所有的 force 加总才会出来的。当你加总之后，就会发现它们两个还是一个作用力跟磁力的作用力跟反作用力还是遵循大小相同、方向相反的。即便在微观的状况底下，它们是没有在相反方向的。Alright. So here are some observations we observed in the Ampere's law of force, Ampere's force law. First, the magnitude of the force is proportional to the product of the two currents and the length of the two current elements. Second, the magnitude of the force is inversely proportional to the square of distance between the current elements, as we can see here. Okay, so the first one is I1 dO1 is proportional to I1 dO1 times I2 dO2. The second observation is that the force is inversely proportional to R to the square. The third observation is to determine the direction of the force acting on current element dO1. We first find the cross product of dO2 cross A21, then find the cross product of dO1 with this result, which can be either of the same or opposite or even perpendicular directions. So the direction is not a given. You need to do the calculation. So for example, dF1, which is the force from dO2, the current on dO2 acting on dO1, is pointing to the right, like the red arrow. For arbitrary orientation of dO1 and dO2, this operation yields dF1 and dF2, which are not equal nor opposite. Their directions is not necessarily of opposite direction. So here are some numerical example. So you should check with this example yourself. Say I1 dO1 is located at position 1, 0, 0. I2 dO2 is located at position 0, 1, 0. Then you can find out A12 and A21 are of opposite direction, like this. And the cross product of any of the source and the connecting lines and the dF1 found out by this result are, for this case, for this example, they are of the same magnitude as I already mentioned. However, dF1 is pointing to AY direction, while dF2 is pointing to AX direction, which means the two forces in this case are orthogonal, 垂直. But this is not necessarily the case. They are not necessarily to be orthogonal, not necessarily to be of the same or opposite directions. It can be anything depending on the orientation of dO1, dO2, and the line joining the two the observation and source points. All right, so here is the illustration of the example stated in the previous page. So you should help yourself find out what is DF1, what is the direction of DF1. Okay, in this case, DF1 is pointing upward to the y direction, and DF2 is pointing to the y, to the positive x direction. Okay, so you should practice with your right hand to find out the correct orientation of the magnetic force. So as this example suggests, DF1 and DF2, even though they have the same magnitude, they are of perpendicular direction. They are not in the opposite direction as the Newton's third law of force suggests. But this is not a violation of Newton's third law because isolated current elements do not exist. They need to be accounted as a whole. So because currents always forms a loop, so the overall effect of magnetic force is acting on the whole loop. So you need to find out the total magnetic force acting to a current loop from another current loop to get the correct observation. And if you do that, the Newton's third law is fine, is okay, it's not violated. All right? Now, the Newton's third law must and does hold for complete current loops. Okay? And so as we have seen from magnetic force equations, they suggest that each current element is acted on by a field due to the other current elements. So we can introduce the idea of a magnetic field. If we have, this says that if we have two complete current loops, of course we can experience or observe the effect of magnetic force. Then how about we have just only one current loop? If we have just one current loop, we cannot observe the action of magnetic force. Nevertheless, the effect, the magnetic field produced by the standalone current loop, still there. So you build up fields in its neighborhood. If you want to observe the effect of this field, you simply bring in another current loop. Then you will observe the effect of magnetic force. So, because of this concept, we can set up the definition for magnetic field, which is usually referred to as H, which is there as magnetic field intensity. Another physical parameter that is closely related to H is B. B is referred to as magnetic flux density, 磁通量密度，上面叫磁场强度，这边下面叫磁通量密度。And B is actually equals to permeability mu that we have just mentioned, mu times H. So B is related to the existence of electromagnetic field as well as the material property of the medium. Well, okay, so that's B and H. In fact, in chapter 1 and chapter 2, we will play more with B instead of H, all right? So, because B can be expressed directly from this equation, if you remove I2DO2, then everything in this parenthesis can be referred to as B1, which means this expression is what? This expression is the magnetic flux density produced by the presence of I1DO1 over here, I1DO1. And of course, K, the constant, is replaced with mu sub 0 over 4 pi. Mu sub 0 suggests that this current section is located in free space, in vacuum. All right, so based on the equation of Ampere's first law, we can derive the definition of magnetic flux density B, and it's in this formation. Then the F2 can be rewritten as the cross product of your observation currents, that is I2DO2 cross B1, cross the magnetic flux density produced by I1DO1. All right? So here's another alternative way. Here's an alternative way to express the magnetic force using the concept of a magnetic field or magnetic flux density. All right, so you can, here is the expression for B1. Equation 1.73 is the expression for B1, which is due to the presence of I1DO1. And of course, you can write up the expression for B2, that is due to magnetic flux due to I2DO2 in a very similar fashion. And DF1 can be expressed as the cross product of I1DO1 cross B2. So that will be the force experienced by DO1 due to the presence of I2DO2. All right? And the last thing we'd like to mention is the unit. The unit is kind of familiar. It's Tesla, right? No, Tesla. Well, I bet that there are not that many people heard of Tesla 20 years ago. Right? This name is a household name, right? Well, one Tesla is about 10,000 Gauss. Gauss 那个是高斯啦，高斯，我们过下个月就会提到高斯了高斯定理嘛，那也是马水科学其中2条，他一个人就占了2条高斯定理。The magnetic field of the Earth's magnetic field is actually relatively small. It's only 0.5 Gauss. So Tesla is actually a very large magnetic force, a very large unit for magnetic flux density. Do you know how large is 1 or 2 Tesla? Well, MRI, have you ever heard of that? The magnetic MRI is M stands for magnetic, R stands for resonance.